Welcome everyone. So I am going to give a lecture on the topic, the role of artificial intelligence in distribution grid control, future prospects and interplay with local energy markets. Here is the outline of this lecture. First, we go through the terminology used in the topic of the lecture. What is artificial intelligence? What is a distribution grid? What is a local energy market? Then we discuss what artificial intelligence techniques are used in the distribution grids. We will then go through problems for local energy markets in the distribution grids and how artificial intelligence can be helpful in those regards. Finally, we shall draw conclusions from this lecture. Let us introduce the terms in the topic of the lecture first. So what is artificial intelligence? While it is tempting, especially in science fiction, to talk about artificial intelligence as computers or robotics with advanced capacity, looking at the definition given from Wikipedia, the term is a broad umbrella covering all sorts of computing and levels of sophistication. One simple way of understanding all the artificial intelligence techniques is to view them as a series of nested sets within one another. Artificial intelligence is any computer that exhibits some form of intelligence. This has a very long history. Then came machine learning, which can learn from historical data. Techniques such as linear regression, logistic regression, decision trees, random forests, support vector machines, and clustering models like k-nearest neighbor all fall into this category. But the most popular type of machine learning is artificial neural networks. Within the neural network category lies deep learning. These are neural networks that have hundreds of layers of neurons. Convolutional neural networks and multilayer perceptrons, for instance, lie within this category. Finally, state-of-the-art in deep learning is generative artificial intelligence that are capable of creating original contents. Diffusion models and transformers are among the most common ones within this category. It is also worth dividing artificial intelligence techniques into the ways they are trained, especially in the context of machine learning. Traditionally, there are three ways to train an artificial intelligence model. In supervised learning, the model is trained with data labeled with the correct answers. The goal of the model is to learn a general rule that maps input to output, and thereby predict the correct answers. Examples of supervised learning are regression models and classification models. In unsupervised learning, the model is trained with data without labels of the correct answer. The goal of the model is to find structure in its input. For example, clustering and feature learning. Reinforcement learning. The model is trained with an interactive environment, constantly receiving reward from its actions. The goal of the model is to maximize the reward by constructing and updating an optimal set of action policies given observation from the environment. Knowing what artificial intelligence is. Next, let us explain what a distribution grid is. To do so, we will refer to this very simplified figure. The power system can be thought of as a complex network with a hierarchical order. At the highest level are the transmission grids, which transmisses electricity across a wide spatial area, say an entire nation. At the lowest level are end users and distributed resources, such as variable renewable energy or batteries. In between, connecting the transmission grid with those resources, are the distribution grids. Unlike transmission grids, distribution grids serve a relatively smaller spatial area, say a municipality. With the concept of a distribution grid in mind, the concept of a local energy market is also easy to understand. A local energy market is a market for trading energy. It is local in the sense that participants all need to be within a certain locality, usually in the same distribution grid or smaller area. So which artificial intelligence techniques are used in the energy system? Up until now, classic artificial intelligence, especially nature-inspired algorithms, such as genetic algorithm, artificial bee colony, ant colony optimization, and particle swarm optimization remains relevant in the literature. However, most of the models used now are machine learning models, such as support vector, decision tree, and artificial neural network, while some deep learning models, such as recurrent neural network, convolutional neural network, and multilayer perceptron, are also being applied. The usage of these artificial intelligence models also grows very fast recently, benefiting from recent breakthroughs in artificial intelligence technologies. But is applying artificial intelligence really worth it? Before we dive into the details of artificial intelligence implementation in the distribution grid, let us first raise the following question. Is applying artificial intelligence really worth it? Generally, there are currently two stances on artificial intelligence. For one group, as shown in this video, they genuinely believe artificial intelligence is the answer to many problems and deploying them widely. Achieving full automation across society can benefit humanity greatly. For the other group, artificial intelligence is a threat to existing jobs and social values. The proliferation of it will cause or enhance problems within society. There is no exception when discussing artificial intelligence and the energy system. Sure, for some, artificial intelligence represents an opportunity to innovate and revolutionize the energy sector. But for others, the increasing energy demand of training and facilitating artificial intelligence is concerning. Therefore, it is always good to think about these questions prior to deploying artificial intelligence in a domain. 1. What is the problem we are trying to address? 2. Why is using artificial intelligence beneficial to addressing the problem? In the context of this lecture, which is to discuss the role of artificial intelligence in distribution grid control and local energy markets, we can try to map out the relevant problems a local energy market in the distribution grid might face. These are the need for accurate forecast of demand and variable renewable energy generation, the need for time-efficient and reliable decision-making either in the market or for dispatching flexible capital. Given that most market participants in an local energy market might not be energy experts dedicated in the market all day long, they need time-efficient and reliable decision-making process when participating in the market and dispatching their flexible capital. The need for a well-functioning distribution grid. Obviously, a local energy market cannot function if the distribution grid it lays in malfunctions. The need for secure and private ways of utilizing sensitive data. In the scale of local energy market, highly disaggregated demand and supply data are needed, which requires extra care in this regard. Now we will go through each problem one by one, discussing why artificial intelligence is beneficial in addressing the problem and how it can be implemented to that end. Accurate forecast of demand and variable renewable energy generation. As shown in the figure, more and more distributed variable renewable energy resources are being installed and integrated into daily life of ordinary people. However, the stochastic nature of electricity demand and variable renewable energy generation means that sufficiently accurate forecast of these variables in the near future is essential for economically efficient scheduling of flexible capital, either for the owners of the assets or the distribution grid and local energy market in general. So we want accurate forecast of demand and variable renewable energy generation. But why exactly does artificial intelligence help here? The main reason is that demand and variable renewable energy supply are related to various factors. So, for example, demand profiles can be affected by household sizes and types, type and size of residence, and outdoor temperature. Solar generation can be affected by solar radiation and temperature. Wind generation can be affected by wind speed, terrain, and large-scale weather systems. Many of these factors exhibit nonlinear relationships with broad spatial and temporal interdependencies. These characteristics make forecasting the profiles suitable for machine learning applications. Here is a summary of recent development in using artificial intelligence to forecast. Classical machine learning techniques remains relevant, as in reference 1. Deep learning models such as long short-term memory recurrent neural network and convolutional neural network are also used, as in reference 2 and 3. Emerging artificial intelligence can increase the accuracy of predictions. For example, transformer-based techniques suitable for long sequence time series forecasting, as shown in reference 4. A single sample of forecast might not be sufficient for stochastic economic dispatch. Based on historical data, generative artificial intelligence can create multiple synthetic load and generation profiles at once for that purpose, as shown in reference 5. Effects of better forecasting in a local energy market. For the local energy market, better forecasting of demand and variable renewable energy supply leads to the following benefits. Better load forecast. In one recent study, average difference to the optimal market clearing price decreases by 45% for 77% of root mean square error reduction in load forecast in one 100 household community. In another 25 household community, 37% of root mean square error decrease in load forecast reduces average difference to the optimal market clearing price by 83%. This implies that the reduction of forecast error is more beneficial when the size of the local energy market is smaller. Better variable renewable energy forecast. One recent study using long short-term memory to forecast variable renewable energy output creates 15% savings for participants in a decentralized renewable energy market, while reducing grid congestion by up to 20%. Time-efficient and reliable decision-making. Why does artificial intelligence help in decision-making? As shown in the figure in the right, compared with human, artificial intelligence can perform routine tasks seamlessly with automated and more efficient workflow. This gives it potential contribution in helping owners of flexible assets to make time-efficient and reliable decisions regarding the dispatch of their assets and participation in local energy market. Why? That is because for professional traders and market operators, conventional optimization methods can be time-consuming, especially if the problem is non-convex. In addition, local energy markets consist of many ordinary households. Households and small businesses might not acquire the necessary domain knowledge to participate in local energy markets on their own. Their dispatch and bidding strategies may therefore rely on simple heuristics. Artificial intelligence can therefore strike a balance between the two extremes. Artificial intelligence can be trained with supervised or reinforcement learning for decision-making. When trained with supervised learning, the correct decisions are labeled on the data using either conventional optimization methods or existing datasets. When trained with reinforcement learning, the model adjusts its policy iteratively to improve a reward function. Here is a summary of recent development in using artificial intelligence for flexibility dispatch. For simple cases, dispatch of flexibility can be formulated as a classification problem. For example, an electric vehicle can be instructed to charge, discharge, or stay idle using a decision tree or a transformer model. Energy demand for training an artificial intelligence model can also be used as a flexibility asset. As you can see on the figure in the right, this would result in artificial intelligence energy consumption aligning more with the production of renewable energy in the proximity. Here is a summary of recent development in using artificial intelligence in a local energy market. Artificial intelligence application of decision-making in the local energy market can be categorized into 3 groups. A centralized approach assumes the market operator obtains all relevant information and trains one single model, as in reference 1. In a decentralized approach, each local agent trains their own model based on their own accessible data, as in reference 2 and 3. In a distributed approach, each local agent trains their own model based on their own accessible data, but the parameters of their models are aggregated to guide updates of each local model as in reference 4 and 5. In the decentralized and distributed framework, agents usually use reinforcement learning to obtain a set of policy according to observation. For the distributed framework, there is also the distinction of coordination offline or online. In the former case, the local models are trained in a distributed manner, but in real-time implementation each agent implements the local model independently, while in the latter case agents communicate with each other also in real-time implementation. A decentralized framework usually converges slower than a distributed framework, which in turn usually requires more time and energy than a centralized framework. However, decentralized and distributed frameworks have advantages over centralized frameworks in terms of security and privacy. Effects of decision-making using artificial intelligence. Using artificial intelligence is much more time efficient than conventional optimization methods. For the dispatch of a few hundred electric vehicles, it can be about a few thousand times faster to use artificial intelligence, as shown in reference 1 and 2. However, the models are usually benchmarked against simple heuristic or other artificial intelligence models. The optimal gap between conventional optimization methods and artificial intelligence is usually not reported. In reference 3, we see that a 60 to 100 times increase in computation speed results in 10 to 25% less objective value of a maximizing problem. Sometimes a convex relaxation can be applied to the original problem, so a conventional optimization algorithm is feasible in terms of time efficiency. Sometimes a convex relaxation can be applied to the original problem, so a conventional optimization algorithm is feasible in terms of time efficiency. If the optimality gap between the relaxed optimal and the objective value obtained from artificial intelligence is small as in reference 4, this indicates that the artificial intelligence algorithm is an appropriate alternative to a conventional optimization algorithm. Well-functioning distribution grid. Why does artificial intelligence help in maintaining a functioning distribution grid? A well-functioning grid is crucial to the normal operation of a local energy market. Artificial intelligence can help in this regard because of these reasons. The failure of critical components is affected by various factors such as weather, age, and utilization rate. Similar to forecasting demand and variable renewable energy generation, nonlinear relationships of these factors make predicting it difficult. The power flow equations of the distribution grid make the optimal control problem non-convex when voltage control is considered. Conventional optimization methods can be time-extensive. During an outage, deciding whether to turn on or turn off switches and controlling critical components is also computationally challenging for conventional optimization methods. During a contingency, obtaining a robust and stable control policy is more important than obtaining the most economic efficient policy. Summary of maintaining a functioning distribution grid using artificial intelligence. The identification of critical components that are under high risks of failure can be formulated as a classification problem, e.g. whether a feeder will very likely to experience outage the next day as in reference 1, or whether a transformer will fail in the coming year as in reference 2. The goal is for distribution system operators to gain more information in the failure probability of the components and act accordingly either through local energy markets or maintenance rescheduling. Real-time fault detection can also be formulated as a classification problem according to the measurements gathered. Simple artificial intelligence such as the fuzzy logic in reference 3 is sufficient to perform the task, although convolutional neural networks in reference 4 have been shown to provide a better performance than classical machine learning. Using artificial intelligence for frequency control is less relevant in distribution grids since the control parameters are determined by the transmission system operators under normal operational conditions. For the distribution grid, more focus is on using artificial intelligence for voltage control. Since the power network can be seen as a graph with buses as vertices and power lines as edges, graph convolutional neural network can be used for real-time voltage control as in reference 5 or outage management as in reference 6 in an active distribution network. Data security and privacy. Finally, digitalization of the distribution grid creates huge volume of data storage, data transmission, and exploitable vulnerabilities for the distribution grid. The usage of artificial intelligence in distribution grid and local energy market applications can be designed using federated learning to mitigate the security and privacy risks accompanied by digitalization. However, artificial intelligence serves as a double-edged sword for cybersecurity in this regard, since both the system operator and the attacker can leverage computational intelligence at their favor. Summary of using artificial intelligence to keep data secure and private. To avoid large flow of data, we can form the artificial intelligence training process in a distributed manner commonly known as federated learning. In a federated learning setting, each agent trains their local model with their local data. Only the model parameters are shared with each other. Usually, a global update of some information of these parameters, e.g., the weighted average of the local parameters or their gradient, is conducted by a central server or a designated worker among the agents. The global information is then broadcasted to all the agents for them to update their local model parameters accordingly. To preserve privacy of local data, encryption methods such as homomorphic encryption or differential privacy are used when transmitting model parameters during federated learning. This can also help keep the system secure from a cyberattacker. Artificial intelligence can be used to detect anomalies within the data, as in reference 1. However, the threat model these artificial intelligence algorithms assume is usually called a white box attack, where an attacker can only perform effective malicious data injection with complete knowledge of the model. With use of generative artificial intelligence, it is possible for an attacker with only knowledge of the output of a grid stability prediction model to learn and conduct effective gray box attacks, as in reference 2. Conclusion. So now we come to the conclusion of today's lecture. In summary, we have the following points. There are many existing and potential applications of artificial intelligence in the control of distribution grids, including accurate forecast, time-efficient and reliable decision-making, maintaining distribution grids' function, and data security and privacy. Artificial neural network and classical machine learning once dominated the research, but in very recent years deep learning and generative artificial intelligence become hot topics. Blockchain and other encryption techniques are commonly applied together with artificial intelligence, especially in a federated learning environment. For local electricity markets specifically, artificial intelligence technologies provide market participants, market operators, and distribution system operators improvement of supply and demand forecast. They can also offer time-efficient and privacy-preserving alternatives to traditional market clearing algorithms based on centralized and conventional optimization methods. However, loss of optimality as a trade-off can often be overlooked. Most literature around artificial intelligence and distribution grid discusses positive synergies between artificial intelligence and the grid. Still, negative impacts should be considered more holistically alongside, including higher energy demand, more sophisticated cyberattacks, social inequality due to differences in computational resources. So, are there any questions regarding the lecture? If there are none, then thank you for listening.